I'm pretty sure people have recorded.
Oh,
Yeah.
Okay. So that looks like the recording has started.
that's weird.
Do people see a recording indicator in the corner of their screen now?
Yep.
All right, you are all informed, and I'll consider staying in the room to be consent. So this talk is Decentralized is not distributive. I decided I wanted to give this talk, even though it's not particularly conventional for this Lightning Talks group, since it's not very security focused, because I have been hanging out in the Blue Skies group. And one of the topics that has come up over and over again is Zuko's triangle. So Zuko Wilcox was a security researcher who talked about the fact that if you want to have names in any kind of system, you're going to have to choose between them being decentralized, secure, and human meaningful. And most of the people are like, oh, blockchain has solved this problem. We no longer need to worry about the way we have names in distributed systems. But to build something like Blue Sky, we want lots of different organizations to be able to build social networks that interoperate with each other. And I do think we, in fact, need to take into account multiple different kinds of names. We can't simply put all the names on some blockchain and call that a day. And I found that the misunderstanding largely came from a discussion of this word decentralized, and that people in the community were not using the word decentralized in a consistent way. And hopefully I could put together some ideas that I thought made that clearer and share them first in this group and then with a wider Blue Skies community if people thought this was a helpful description. So to begin with, let's explain Zuko's triangle. There's three things you want in any name in a distributed system. You want those names to be secure. When I refer to something, I want to make sure that you get the same thing when you put in that name as I'm referring to when I use that name. So names should be mutually exclusive to each other. The second is you want it to be decentralized. If I make a new thing, I just created a post, I should be able to give some kind of ID to that post without needing to do some global consensus, get the entire world to agree on the name that goes with my post. And the last one is you want to be able to get human meaningful names, or as I like to refer to them, arbitrarily selected names. My system might have a good reason to want to use specific naming schemes. But the problem is you can't actually have all three of these things at the same time. So we end up with three different types of names that we reach for. We have fingerprints, which are something which is unique and can really refer to a particular post. For example, the SHA hash of that post, and is consensus free. I don't need to talk to anyone else to figure out what the SHA of my post is. I can just calculate that number and I know it and I have the fingerprint. The second is addresses. So addresses, aaron@gmail.com is mutually exclusive. It refers only to me, but it doesn't have this ability that I can just generate it myself in a consensus-free way. I'm going to have to go to some kind of authority and say, hey, Gmail, is this name available? Can you give it to me? I have to deal with that centralized authority. And there's limits to my ability to arbitrarily select that name. So Google can give me Aaron at Google, but can't give me Aaron at Hotmail because they don't own that piece of the namespace. So where does this limitation come from? It's basically just a specific application of the CAP theorem. Anytime you have a decentralized system, you're going to be balancing off consistency, availability, and partition tolerance. So if I want something to be both consistent and available, I need to have it exist in exactly one spot. If there is one memory address on one computer that has a particular value in it, and I'm on that computer, I can just change that value. And I don't have to worry about being consistent because there's only one thing. There's nothing to be consistent with. And I don't have to worry about it being available because it's in my local memory and I can just interact with it. The disadvantage of that is I can't scale. If that computer crashes, the value is lost. If I want to have a large number of things that all have access to that value, they would each have to message the one thing and keep getting the message back. And that's not going to scale for either reliability or performance. So we need this partition tolerance. And now we're in this world of choosing. Do we want consistent values or do we want available values? The idea behind this talk was largely inspired by Rob Pike's talk, Concurrency is not Parallelism. He found in a similar way, as he was trying to explain Go's concurrency system to people and how it accomplished stuff, that people would get very confused at the difference between this concurrent, I want to break up my program into lots of small pieces that I can think about well, versus the parallelism, things are actually going to run simultaneously at the same time. In that same way, I think having a talk where we go into what does it mean for something to be decentralized versus what does it mean for something to be distributed can help clarify this somewhat. So let's start with the fundamental mathematics of what we're talking about here. What does it mean for a function to be a distributed function? And there is a relatively straightforward mathematical property for it, and it's that we get these three subproperties. A function is distributive if it is associative. So I don't actually care the order in which I perform the operations. So if I first add A and B and then add C to it, or first add B and C and then add A to it, I'm going to get the same answer because this is an associative operation. You need to be commutative. If I switch the patterns for A and B, I need to get the same answer. So A plus B is going to be the same thing as B plus A, but A to the power B may be different than B to the power A. 2 to the 8th is not necessarily the same thing as 8 squared. And the last is you want it to be idempotent. As I continue to add the same thing more and more often, it's going to change. So here we can tell that addition is not distributive because if I add 1 to 1, I don't get 1 back, I get 2 back. Whereas something like a set union would in fact be distributive. If I have a set containing A and B and I say, great, I'm going to union it with another set containing A and B, I still have the set containing A and B. And if I union that with another set containing A and B, I still have the set containing A and B. So something like a set union is going to have all of these properties that we want to build distributive data structures and enable us to build systems that are going to give us the kinds of eventual consistency that we want without forcing us to always take the performance hit of talking to a central authority or running a consensus algorithm. On the flip side of that, we have consistency. So what is going to make it so that something can't possibly be implemented in a distributed fashion? And there's 3 main abilities that will let you know that you're dealing with a system that requires strong consistency and can provide strong consistency. Those 3 things are mutex, mutual exclusion. If I have some resource and I want to make sure that exactly one entity can have that resource and no one else can. So the classic example of this is airlines. Airlines want to sell all the seats on the plane, but they don't ever want to sell 1 seat on the plane to 2 people. They want mutual exclusion of that seat. They've only sold that 1 seat to 1 person. And they're going to need a strongly consistent system in order to make that work. And if you have a system that gives you the ability to do mutex, you can use that mutual exclusion to build strong consistency. So this is what we do with locks. Our operating system provides us with a mutual exclusion lock, and we can build distributed systems out of that. The second is CAS, compare and swap. If you can have 1 atomic unit where I say, here is the placeholder for a value, and I can swap the value is in that place if and only if some previous value was there, that atomic compare and swap is also one of the bases that you can use to provide a consistent system. And of course, if I have atomic compare and swap, I can use that to make a mutex and say, okay, if I own the lock, I'm going to take this thing. And if I don't own the lock, then I can't act on the thing. And if the lock is unowned by anyone, it'll be swapped to me. So if I assign all of my threads a thread number and say 0 means the lock is unlocked, I can do an atomic compare and swap and say, if the lock is 0, make it my ID. Now I've claimed that thing. If it's not 0, then don't do this. So that lets you build mutex out of CAS. And the opposite. if I have some particular value and I can use a mutex to lock it, and then I can change it, I can build a compare and swap by locking the thing, doing my compare, doing my swap, and then unlocking it. And the third one is a ledger. If I have a log of events and I want to be able to add something to the end of the log, this one feels a little different to the other two, but is actually basically the same, because what is the mutex giving me? Well, it is a successive series of entities that have access to the critical region. What is the cas? I'm swapping exactly from one previous value to the next value. And when I append to a log, whatever was the last thing in the log is now second from last, and I get a strict sequence. So anytime you see a system that's got sequencing in an order, compare and swap or mutex, you know that this is something that you'll never get to fit into a truly distributed system. And that's a time when you're going to want to reach for a strong consistency primitive. So let's talk about blockchains. The main reason people thought, oh, we don't have to worry about this consistency availability trade-off anymore was because now we have blockchains. And that's going to enable us to solve the double spend problem and get a nice distributive mutual exclusion. But the fact of the matter is, blockchains don't actually offer this. They just offer making it really hard for you to get forks. So if I have something like the Bitcoin chain, there's lots and lots of people trying to mine the next block. And when someone has solved the work problem, they start with their next block and start trying to inform people. And if they get a large percentage of the mining community to recognize that they found the next block, we can move on to the next block. But if two people find a solution to the problem, proof of work problem, at about the same time, and they start telling people about it, you can get to a point where about half the world went one way and about half the world went the other way. And now we have a fork in the chain. Now, fortunately for us, Bitcoin doesn't stay forked. Eventually, one of these two chains will win, and one of these two chains will die and go away and not end up being the future. And the double spend problem happens with, what if I spent my coins on both chains at the same time, and then when this chain went away, I'm sort of forgiven. Any money that I spent on the chain that died and went away, I got those resources essentially for free because I didn't give up coins. I spent coins on a chain that died. So this is eventually consistent, and is eventually consistent because it has a distributed function, which is max. If I'm doing max, I have all of these properties. If I say max of 1 and 2, I'm going to get the same answer as max and 2 and 1. I can swap that. If I say max of 1 and 2, and then I max that with 3, or I say max of 1 and a max of 2 and 3, it doesn't matter the order in which I do max. I'm always going to get the same answer back out of my maximum. So it satisfies all three properties of distributive. Max is in fact a way we can do this, and simply saying, hey, max length of chain enables us to always come back to an eventually consistent system. So despite the fact that blockchains are really thought of as a way to get a globally consistent object, it's actually eventually consistent. On the other end of the extreme, we have Crdts. This is a class of data structures that people have built up where they really go deep into the distributive functions and say, let's build something that can satisfy all of these properties and get increasingly complex. So can I build an account for my bank object that is going to be distributive? Can I build an object that is a message post? To some extent, things like email are naturally large distributed things because it doesn't matter what order two people send you emails in, you're going to get those same emails. If I'm sending an email, if Alice is sending an email to Bob and Charlie is sending an email to Denise, we don't actually care about the ordering of which of those things happened first. So we get this distributed system. And increasingly, we're starting to use these. A lot of people feel like this is why that systems like Git enabled us to have a more distributive workflow, and that really empowered open source. One of the reasons that open source didn't really take off in the world of SVN was you were always having to lock things and work on one file, and it would be very difficult for people who were in distributed locations to work together on a project. But when the world switched from things like CMS and SVN to things like Git, now we got an explosion of open source software because it was actually very easy for people to make these local changes and then merge or rebase only at the times when they wanted to. And then the remaining one is, okay, so if the blockchain doesn't give us strong consensus, how do we really get strong consensus and know that, for example, I want to build my airline flight system that really will give exactly one person this seat and no one else, really will sell exactly one person this Airbnb, or give exactly one person the right to book a particular room in a calendar. And we have two main consensus programs that have become popular. We have Paxos, that has at its heart feels like a mutex. I am going to send a message to all of the acceptors and say, don't accept from anyone else. Promise me that you are giving me the exclusive right to make the commit. And then I send my commit and people accept it. So it very much feels like a mutex, and that comes from its history. So it was based on the Paxos Islands in Greece that had a parliament, where the structure of their parliament was that people were on boats and were not there at any one time. So it was not convenient to hold a vote. So instead, they would have one table in the parliamentary house where you would put each of the bills that needed to be passed. And one at a time, when people were in town, they would come in and they would vote on all of the bills. And once a bill had either 50% plus one that said, yes, this should pass, or 50% plus one that said, no, this should fail, then the bill had succeeded or failed, but it could just sit there waiting for 51% of the people to come and weigh in on it. The second one is Raft. So I went looking to understand what is Raft and where did the name of Raft come from. So it turns out that the original name for Raft was the tied logs protocol, or synchronized logs protocol, because each of the servers is just accepting new messages and appending it to a ledger of what's going on. And when two people get out of sync, whoever's got the longer ledger will catch up the person who has the shorter ledger. So it is a series of different logs that are each being tied together. When they went to write the paper, one of the authors decided that synchronized logs protocol was not very catchy. What do you get when you tie a bunch of logs together? Oh, it makes a raft. We'll call our protocol Raft. So Raft is very much this ledger idea at its heart, and tied those together. And most people seem to feel that Raft is a much simpler protocol to understand, because ledgers are just more in line with the way human brains seem to work than mutexes are. Whether you're doing a distributed system or even multiple threads on one computer, mutexes and locks tend to get people in trouble. So to summarize, when we are trying to decentralize something and someone says, hey, I have built this decentralized system that is going to empower individuals to make their posts, and we're going to have lots of different networks, and they're all going to be able to cooperate with each other, stop and think about what they're building and try and decide, okay, is this decentralized thing that they're promoting actually a distributive system or actually a consensus system? And for the things that they're promising, do they want a distributive system or a centralized system? As a general rule, I suggest we should be using distributive systems whenever we possibly can, because they're going to scale much better and they're going to be much more reliable, because you can't have some number of nodes that are down. If I have a system that fundamentally has a function like max at the top, I can generate a whole bunch of work locally and just send the one maximum result that I have back to anyone who comes to me and says, hey, what is the maximum of the states that you've seen? It makes it very easy for something to go offline and do work and come back online. If I have some application that is on my phone and I lose an internet connection, if it's a truly distributed system, I can continue working on my own and generate new values and new posts and new interactions. These are the things I've liked. And then when I connect back to the network, I can just sync back up with the world. Whereas if I have a non-distributive system, even if it's decentralized, I may find that offline is just as much of a burden and that things can't really scale. There is only so many transactions per second we are able to put through something like the Bitcoin network, because fundamentally it is a consensus algorithm. And we are going to, as a society, have to all come together to move that ledger up, each one. You can't really take those actions on your own. If you want to read more about what kinds of things can be done with each of these, learning about linearizable consistency really is the property that you want from your non-distributive systems to have true consistent behaviors and provide things like mutual exclusion. So for example, if you have bank accounts and you want to make sure that someone can spend their money once but can't spend that money twice, you're going to need mutual exclusion. And the best we can do if we have a distributive system is transactional causal consistency. So we can get a world that looks totally reasonable, where every message you've seen and you reply to, we can actually guarantee causality in those systems and get systems that can be reasoned about in a sane way. The only things that we can't provide is strict linear ordering, mutual exclusion, or a pure compare and swap. So lastly, I want to go over some systems that you can think about and say, okay, are these things distributive or non-distributive? And are these things decentralized or centralized? So we definitely have centralized aggregative things. Shared memory. If you've got two people who are just hammering on the same memory address, they're going to have to be careful not to clobber each other, because that's a very centralized system. And there's one truth, but you can still get mistakes there. A Unix file system. If you are using that as a way to share, you tend to be writing to it, and there's going to be one source of truth, and it's basically going to be last writer wins. A serial database. So something like SQLite. How does SQLite manage to give us these ACID properties of independence between transactions? It's simple. It gets linearizability by being linear. It executes one transaction, and then the next transaction, and then the next transaction. And because no two transactions ever operate simultaneously, it doesn't have to worry about it. It gets a strong, linearizable consistency because it's actually doing all the things linearly. Like, that is the definition of correct. And object-oriented was there a question?
Yeah, Aaron, just want to add about one thing, linearizability. What linearizability says is, like, there is it doesn't exactly say that execution is one after the other. There are multiple parts of the different transaction that part of them can happen concurrently. What the definition of linearizability or even opacity is that, however, the order of completion is such that you can put them and in an ordered timeline, ordered points on a timeline. So there is some level of concurrency as long as there is no concurrency conflict.
Yes. So for example, in SQLite, it gets linearizability by actually doing them in a linear order. For example, something like Postgres is going to be executing transactions in very much out of order and only gets the linearizability because it's following an as-if rule. All of the transactions are executed as if they had been in some linear order. But did this one actually finish before that one? Maybe, maybe not. There are no real guarantees about true time, just that the end result of your database is a state that the database could have gotten into given some linear ordering of those events. And we have things like version control. So Git, I think, got us a long way toward having distributed systems. Now, it's got a very expensive merge function to enable to get there, which is, it says, hey, if I'm trying to merge two things and I've got a merge conflict, hey, you human, fix it. Crdts are a lot easier to use because we've made a priori decisions. We've done the math to say, when these two things meet, here's how they're going to aggregate with each other. Maybe it's first writer wins. Maybe it's last writer wins. Maybe it's max in some way. Maybe it's a set union. And we are building more and more CRDTs all the time to enable us to choose merge policies that we like that can operate without a human stopping and saying, okay, let me show you exactly how these things will in fact merge, and handling the merge conflicts ourselves. I consider Git to be distributive even so, because it does have this ability that says, hey, if this commit descends from this commit and descends from that commit, it will trump both of them. So once I do my merge now knows that it has two parents and will replace both of them. And when I send that to some other server and it sees that, it can say, oh, I'm on track A or I'm on track B. I don't care which. I'm going to go to the new commit because the new commit is downstream from both of those. And the last is to look for functions. Like the pure math doesn't actually care whether it's centralized or decentralized, whether you do an aggregative solution or a distributive solution. But the math has those properties. If I'm anding a bunch of things together, oring a bunch of things together, union, intersection, max, min, greatest common denominator, least common multiple, or factorization, these are all mathematical functions that we can use to build systems that are these. And you can get what looks like strong consistency with something like a blockchain in the absence of a 50% plus one attack. So finally, going back to where I started, I think that as we are trying to build these new social networks that are able to interoperate with each other without one centralized thing, we really should not lean toward, let's make one big blockchain that is going to be the blockchain of all the social networks, and it's going to hold all the names, and it's going to solve a lot of these problems for us. We really are going to have to find distributive solutions that enable these different networks to talk to each other without needing to come to one consensus view on what the world looks like. And that means we're going to need fingerprint names where you just have the hash of someone's certificate. And I can take that with me from network to network and say, hey, this is who I am, and I can prove it. You give me a nonce. I'll give you your nonce signed by my public key and a certificate containing my public key whose hash is this fingerprint. So now I can take this one fingerprint with me to any system in the world. As long as it can do math, I can prove to it that, in fact, that fingerprint is me. We need systems like addresses, where there really is a consensus authoritative answer. Saying that I am A. Goldman at Twitter is something that only Twitter should be issuing, and Twitter should be able to revoke if I ever leave. In the same way, you're going to want to have distributed systems where an authority can grant some particular assertion, and that authority can retract that particular assertion. And this is going to be these address styles of names. And thirdly, we're going to need tags. Some people have argued that you don't need arbitrary tagging, because what if two people just claim the same tag? Like, we don't have mutual exclusion at that point. If I say, this is my fingerprint and my name is Aaron, and I say, this is my fingerprint and my name is Goldman, and I say, this is my fingerprint and my name is Aaron Goldman, well, there's about 200,000 Aarons in the world. There's about 50,000 Goldmans in the world. There's almost 1,000 Aaron Goldmans in the world. But it's still useful for me to tell people, hi, I'm Aaron Goldman, because it narrows it down a lot. If you go and you do a search on LinkedIn for Aaron Goldman, yeah, you'll get a lot of Aaron Goldmans, but you'll pretty quickly be able to figure out which one is me by other assertions. This is the Aaron Goldman who worked at Google and worked at Twitter and likes to do distributed systems things. So we're going to ultimately need all three kinds of names in a distributed system like Blue Sky, where we have fingerprints that can be totally consensus-free and securely mutually exclusive, addresses that are mutually exclusive because some particular authority is standing behind them, even if that authority is a blockchain as a consensus algorithm. And we're going to want people to be able to just put arbitrary tags on them to enable search. And once you can narrow things down and identify the one who you want, great. Then add your fingerprint to the address book. All right. With that, are there any questions or comments that people have? If not, I will stop the recording and then ask again. Thank you very much for your time.
This is a very good, Aaron, and thank you for